Hi, I'm Leif Peterson, and I'm going to go through version 22 of NXG Logic Explorer. As you're aware, Explorer is a data analysis package that will perform summary statistics, association analysis, independence and hypothesis testing, dependency, class discovery, feature selection, class prediction, survival analysis, text mining, and Monte Carlo simulation. Here is shown a new workflow that is incorporated in version 22. A new dark and light display mode option has been developed so that users who like a dark display can do that, or a light display. So that's available now. With regard to the workflow icons, there are a series of data and feature selection icons shown here at the top. A set of summarize icons, a set of feature transformation icons that can be dropped onto the workflow. Here I show the association icons. Here are the independence and hypothesis testing icons, and the dependency or regression and boosted regularized regression icons. Here are the workflow icons for survival analysis, class discovery, or unsupervised analysis, feature selection, class prediction, and some graphic icons that can be dropped onto the workflow. You notice there were two small icons in red for data input, so several types of data can be entered or input into Explorer. These include Excel files, comma delimited files, tab delimited files, and Microsoft Access or SQL databases. There's a blue data mod or data modification icon, which allows one to input a series of logical if statements or in syntax to create new features, to delete features, to create new features based on mathematical transforms, and also to drop records based on filtering through a set of logical if-then statements. And there are also two orange icons, one for grouping and one for filtering or subset analysis, that can be dropped on the workflow. There's a help icon that will show this pop-up of a series of icons used in sequence for any given type of analysis. So this is a quick reference guide for users learning how to use NXG Logic Explorer, or those who forget to do a certain task. With regard to summary statistics, NXG Logic Explorer performs parallel feature analysis. It determines the mean standard deviation, min-max range, quartile skewness, and also automatically performs a Shapiro-Wilk test of normality for continuously scaled features. It generates categorical frequencies, generates histograms automatically, and it's a considerable time saving when you have to do a lot of rote, mundane, non-sophisticated statistical analysis for a mixed set of continuously scaled and nominally scaled features. Here are some categorical frequencies over here, the icons for a summary statistic run, and then the variable listing or feature listing inside the program. Here is a summary statistics output table for a data set that had 14 features, 3 of which were categorical. The rest were continuously scaled. The sample size was 314. There were no missing data in this data set, so all the sample sizes are 314. Here is shown the average, the standard deviation, min, max, range, median, the Q1, Q2, and Q3, which are respectively the 25th percentile, the 50th, which is the same as the median, and the 75th percentile, the skewness, kurtosis, and the p-value from the Shapiro-Wilk normality test. As I said, Explorer automatically generates histograms for the variables input into a summary statistical analysis. So here we see the variables for that data set. Explorer will also perform feature transformations, and these include normalization, standardization, logarithms, base E, base 10, or a custom base, quantiles or new categorical variables or binary variables from categorical levels, a rank transform, a percentile transform, van der Waals scores, which are based essentially inverse cumulative normal variates based on percentiles. And one can see here the output icons when a given transformation is run. Here's a listing of the variables. When one performs transformations, if you normalize features, as an example, these three normalized features here, they begin, the variable name or feature name begins with an N. If you mean zero standardize, a Z is used. If you log, the base is written after log. If you use quartiles, the Q is shown here. Ranks, percentiles, and van der Waals scores. And then this shows here a plot of those variables after they were transformed. And obviously the van der Waals scores are all standard normal distributed. Explorer will perform grouped analysis and also subset selection or filtration of records during workflows. Here is shown the grouping icon, which will allow a user to right-click on this and select the multiple groups that can be used for the entire downstream grouping analysis. Here we're performing multiple linear regression on each of the groups. If statements can be used to define groups. And here is the filtering or subsetting icon. And again, here we're doing a downstream correlation analysis on records or observations that were filtered from the data set. And as an example of a logical statement, here you could select age records for filtration for which the age is greater than 50. The gender was a 2, or the subject had a smoking status of 1. With regard to association analysis, Explorer will always calculate the Poisson and Spearman correlation coefficients and generate correlation coefficient tables. It will also output an image of the p-values based on colors, and then a force plot for each method. And one can also come along and perform covariance analysis to generate the matrix, and Euclidean distance to generate the Euclidean distance matrix. Here's an example of a Poisson correlation matrix for some continuously scaled variates, and there are some certain colors, the reds and pinks and blues and lighter blues, used for significance of the coefficients. So the coefficients themselves are shown here with asterisks used to denote level of significance. And here is shown the various color scale of a Euclidean distance matrix. This is the significance matrix, which essentially just shows a color for a pair of features if the correlation was significant. So again, this is done for Spearman and Poisson. These are very helpful to generally just show plots of what's correlated, irrespective of the correlation coefficient. And over here is shown a force plot. With regard to independence and hypothesis testing for 2 and k samples, t-tests, Mann-Whitney are used. There's a test for 2 proportions. There's a paired t-test and a Wilcoxon sign rank that's applied simultaneously. And then the McNamara test can also be used for 2 matched binary vectors. For 2 sample test, here is shown an output of t-tests and chi-square contingency table tests for a categorical variable, and 3 binary variables against the 0-1 outcomes in the low birth weight data set published by Hosmer and Lemechow. There's 189 records, 59 of which involve women who gave birth to a low weight baby whose weight was less than 2,500 grams. So if we look at these variables, you have the mean here, the standard deviation, mean standard deviation for each group, the t and the degrees of freedom, the p-value for the t-test. Explorer will also output the Mann-Whitney z-score and the p-value, and then it will also perform an equality of variance test or heteroscedasticity or homoscedasticity test using Bartlett's chi-squared test, and then report the p-values. So blue p-values indicate not significant below a level of 0.05, and red indicates significant with a p-value less than a 0.05 for a type 1 error level. Now, when one performs a chi-squared test, you're essentially testing differences of the column-based frequencies. So the columns within the group across the levels of a categorical factor, the column frequencies always sum to 1. So you can go across all these this nominally scaled variable here and these binaries, and they all sum to 1. 0.66 plus 0.34 is 1. 0.49 plus 0.51 is 1. So the column total sum to 1, and you're essentially testing for differences in the the observed and the expected values of the count frequencies, are essentially the proportions in those tables. Here's a output for a K-sample test involving 3 groups. This variable was called smoking status. It was in a retinol data set. There were 2 categorical features here. Actually, there's a categorical icon shown here because the input data were not binary, but rather 1, 2. And then for the categorical, you had a 1, 2, 3 here. And the rest were continuously scaled. If you go through this, you want to look at the Bartlett's p-values first. So here it's a 3-group test. Bartlett's was significant, so therefore the degrees of freedom in the ANOVA were altered. And it's essentially the Welch ANOVA test. If it's when Welch is not used, it's a standard ANOVA, for which you can see 311 is the degrees of the numerator degrees of freedom is 2, and the denominator degrees of freedom is 311 here in all these cases, except the degrees of freedom changes whenever Bartlett's is significant because you're performing a Welch test. So again, for the 2 sample tests, you're performing a Welch test whenever Bartlett's test is significant. That is, the variances across these 2 groups within the variable are significantly different. And otherwise, the straightforward student's t-test is used. But Explorer does always test heterogeneity of variances. So one really doesn't need to test. Variances are assumed unequal, not really assumed equal, but they're tested. So the program doesn't really ever assume equal variances. Here are shown the results of the 2 proportions test. There are 2 statistics used, the unpooled Z and the pooled Z. And then for McNamara test, which is a test of paired binary vectors, you have the counts for negative and positive, or before and after. And Explorer will also show the percent of subjects that switch from one to the other. Now, with regard to multiple linear regression and multivariate normal regression, Explorer will do both and will also perform regularized variants of these 2 types of linear regression. When linear regression is run, you get an output of the coefficients, the residuals, the DF betas, and the variance inflation factors. And when multivariate normal regression is run, you get the full model test, feature test coefficients, and a listing of the significant coefficients. So you have the studentized and the standardized residuals, the DF betas, Cook's distance, DF fits, and then the VIFs. And also Explorer can output either the predicted y-hats or the residuals from a multiple linear regression run or a multivariate normal regression run. For multiple linear regression, every analysis starts with a univariate linear regression run of all the features by themselves to generate the p-values, which are compared against a cut point p-value or a threshold p-value as a candidate for entry into a multiple variable model. And one of the strong things about Explorer is that for any categorical variable that's used or specified for a multiple linear regression model, or for that example, any multivariate normal run, logistic run, or a Cox proportional hazards regression run, any categorical feature that's used will have all of its levels transformed into k-1 binary features. And as I said, Explorer will run the model building strategies, MBS, using p-value cutoffs from the univariate linear regression. And then after univariate linear regression models are run, the multiple linear regression model is run with the variables simultaneously, so it's a joint model. You get an ANOVA table, the coefficients. Now the coefficients can be filtered according to a p-value result, or the p-value for the table can be set to 1, and then you'll have a multiple variable output table for all the features that were used. Partial f-tests and partial correlation and determination are also calculated during a multiple linear regression run. For multivariate linear regression, of course, there are multiple dependent variables. And here I have shown an output table for a regression variable, one of the dependent y variables. It was called beta diet, and then the coefficients. And here you can see that Explorer recoded the gender variable into 2. It only used a binary vector for the second group because the first is a reference cell. And then smoking status had 3 levels, but the first is a reference cell, so there's not a coefficient for it, only 2 and 3. And then vitamin use was also a 3-level factor for which only 2 binary vectors were used. Again, that automatic recoding really helps move the productivity much faster. Now moving to logistic regression, Explorer will perform binary and polytomous or polycotomous with multiple classes. So what is output at the beginning is a univariate logistic regression model for which the p-values are collected and compared against a threshold or cut point, and then a multiple logistic regression model is run with the odds ratios consisting of exponentiated coefficients and their confidence intervals. A Hosmer and Lemeschau goodness of fit table is also generated, as well as the chi-squared goodness of fit, number of patterns and degrees of freedom, and p-values for goodness of fit of the multiple variable model. For polytomous logistic regression, the classes are run in a univariate fashion first against each output variable. So this smoking stat had 3 classes. So you really only get coefficients for class 2 and class 3 for polytomous logistic regression. You don't need a class 1. And same thing here, the outputs commonly for polytomous or multi-class logistic regression only provide tables for classes 2, 3, and so on and so forth. But there was a recent change to generate coefficients for class 1, which are essentially just the constant terms. Explorer also performs Poisson regression. It can run additive and multiplicative and also geometric mixture models. Deviance and Pearson residuals are always calculated because deviance is used for each iteration. The DF betas are calculated and the relative risks. Here's an output of a purely multiplicative Poisson regression run for which the deviance goodness of fit is used for the convergence criteria. This happened to be a model for the British doctors' lung cancer data, in which all these variables are binary 0-1 coded, just to pick off the specific age that the subjects were in, and then smoking 0-1. So you do exponentiate this coefficient to get the relative risk of the smoking coefficient. You can also run a geometric mixture model, in which case Explorer will run all the Poisson regression models from a purely multiplicative standpoint down to a purely additive standpoint. So a value of rho is used in geometric mixture models, and you can then just hunt down the lowest deviance value And for this model, it occurs at 0.55. So the best Poisson model is somewhere between, almost halfway between a purely multiplicative and a purely additive model, which is quite useful for hunting down and tracking the best fit for Poisson regression. For survival analysis, one can perform Cox PH or proportional hazards regression and Kaplan-Meier analysis, and then follow up with longitudinal regression for repeated measures. Whenever Cox proportional hazards regression is run, you'll get an Excel icon for the risk sets, the coefficients, and Explorer will test the proportional hazards assumption using the Schoenfeld residuals. And then Explorer will also generate 3 plots of the residuals from Cox PH regression. When Kaplan-Meier analysis is run, you naturally get a plot of the Kaplan-Meier survival curves and a log rank test output table. So Cox proportional hazards regression runs the univariate models first and then generates the p-values, and then they are used, again here, anything that's categorical that's input into the variable will be recoded into k-1 binary features or binary vectors and then used. Here's an output for a multiple regression model after the univariate models are run, and then variables that were worthy enough or valid enough to make the p-value cut point for entry into the multiple variable model were used. And we can see the output coefficients here. And here is a listing of the chi-squared variates based on the Schoenfeld residuals to test the proportional hazards assumption for each one of the variables that were used in the multiple variable model. And then there's obviously the global test. And we can see here that the second level of the edema categorical variable was close to really breaking down. It wasn't significant. Nevertheless, I would probably drop that feature from the model or else run a stratified Cox regression model. And then hazard ratios are calculated for each of the for all the reported coefficients. Here are the 3 residual plots from Cox PH regression. First, you have the Nelson-Allen residuals versus Cox-Snell. Then the deviance residuals versus the risk score, and Martingale residuals versus the follow-up days. For Kaplan-Meier analysis, you obviously have the plot of survival curves as a function of days. Here's the survivorship function on the y-axis. And then the log rank test has the observed and expected number of failures or events that were observed in the data set, and the chi-squared statistic and the associated degrees of freedom. Now for longitudinal regression, Explorer will run GEE. The user has to make an assumption about the assumed correlation structure of the outcome variance matrix. So one can select exchangeable correlation, autoregressive, independent, which is the identity matrix, or an unstructured correlation assumption. When running GEE or longitudinal regression in Explorer, you'd select the dependent outcome variable here, the time feature, the cluster ID or the ID feature or variable for the subjects, and then the interaction between the treatment and time, and then select all the variables, including the clustering variable here, but not the outcome variable, and then run it, and you'd see during the iterations the error decreasing to convergence, and then in the output table you'll have the dependent variable listed, the probability family listed, the length that was assumed listed, the assumed correlation structure, the scale parameter or phi, which is used exclusively in GEE regression, the number of observations, the number of clusters, and the chi-square and the Wald test here for a simultaneous test that all the coefficients are equal to 0. That's a little bit, it's similar to an F test for ANOVA for a multiple linear regression model, except wald test is commonly used for logistic and GEE, and also can be used for Cox PH regression as well. And then finally, you have a listing of the coefficients. Now for class discovery, Explorer is quite strong in that it'll perform a number of nonlinear manifold learning modules or methods to the data set to try to identify patterns in the data through visual clues of formations of clusters among the objects. So when getting started, if a method uses distance functions, the user can specify which one they want to use. And some methods use a reference vector, like self-organizing maps, or learning vector quantization, LVQ, uses reference vectors. You can also transform the features that are used in these models using mean zero standardization, normalization, or leave it raw. And you can also smear for the reference vectors. Now, what's important in these runs for class discovery is setting the specific number of dimensions that you want to reduce the original input features down to. So here we're setting 2. And then methods that use iterations before convergence, or at least to a small value of some type of an error, you can set the iterations here. So 500 seems to be a pretty good number. Here's an example output of stochastic neighbor embedding, the T variant of that for the 3-class wine data set. And if two dimensions are used, you can obtain score plots for all the methods used and also overlap plots for all the methods used. Here are 4 output score plots for a number of runs that were used. This happens to be self-organizing maps here. As you know, this was a 10 by 10. There were 10 rows and 10 columns. So these are all a reference vector in self-organizing maps. And then the objects move to fixed reference vectors. There are a variety of self-organizing maps, but Explorer uses the variant for which reference vectors are fixed on a map grid, and then the objects migrate to the vectors. It's essentially a prototype learning method. Laplacian eigenmaps seems to do a good job on the 3-class wine data set. This is also the 3-class wine data set as well. And unsupervised neural networks does a pretty good job. This is called an autoencoder. And this happens to be an output shot of the score plot from the 10-class run of about 3,000 records, having about 68 feature values that were extracted from handwritten images of digits 0 through 9 that were collected from test subjects during a research protocol. And you can see that stochastic neighbor embedding does a really good job at agglomerating them into different clusters. As I said previously, when you specify that the features be reduced to 2 dimensions, you'll get a 2D score plot, which is a composite that includes panels for all the methods that were used. So the input data set for this run was a class prediction data set for which the truth label, the true class, was known for each object, and therefore a color can be ascribed to each object. So you have the blue, gold, and red used for the 3 classes respectively. And then you can go through the various methods and look for class separation of the true classes that are in the data. And it just depends. These results obviously depend on the data, and they depend on the methods used, and not so much the feature transformation that was applied, because feature transformations, when you go from mean zero standardization to normalization to even using percentiles, you commonly won't see real large jumps in the disparity between results from one of these methods to the other for the same data set. But the data set used really dictates what happens with regard to each one of these methods. Not so much features, feature transformations used, but the features that are used, whether or not they're noise or significant predictors of class, will make obviously a large difference in what is obtained here. Now, feature selection can be used once class discovery is run. So if you get a handle on features that are predictive of class, you would use feature selection, and the user can specify t-test, Mann-Whitney, Gini index, information gain, and you can use all possible class pairs or one against all. This is where you could, as an example, do a t-test between feature means of one class versus 3 classes combined or 9 classes combined. So that's called a one against all. There's also an all against one, which is essentially the same thing, but there are a variety of these which can be used. Now, regarding the features that you want for the output from feature selection, you can specify the best rank n, or as in this example, you could select the top 5 features that are the best predictors of class. You could specify that you want a p-value used for the t-test or the Mann-Whitney. Or you can use greedy plus takeaway, which is a forward-reverse sequential floating algorithm that is based on the Mahalanobis distance and ratios of Wilks lambda from multivariate full and reduced models to come up with a best set of features that from a multivariate framework and Mahalanobis distance are the best predictors of class. For feature selection is a table of the mean deltas across groups 1 and 2, or classes 1 and 2 for the features, and then the mean t for the t-test was run here with the p-values. And then you can also look at a table of means if you want to, and then highlight these and color these means and look at features that result in the greatest color of means. Then you can also get an output file that Explorer created based on the features that were identified, and then the class variable is also output in this data set used, which can be saved and used in a future analysis for when the desire is to only consider features that best predict the classes that were used. Now, obviously, again, for feature selection, you want to use a class prediction or a classification feature set for which the true class labels are known for all the objects or all the rows or records in the data set. Now, after class discovery and feature selection are run, you can then follow up with class prediction, which is classification analysis or supervised analysis. And Explorer will run k-fold cross-validation, leave one out cross-validation, 0.632 bootstrap, and then also a bootstrap sampling scheme. And then for class-specific outcomes, you can have the sensitivity, specificity, predictive value positive, predictive value negative reported, and then the class pairwise receiver operator characteristic curve area under the curve, as well as an AUC plot generated. Explorer will perform ensemble classifier fusion to fuse together the committee votes of the classifiers that are used, and Explorer will also generate a kappa value and an error value for all possible combinations of classifiers used on that data set, which are output to a spreadsheet that can be which the data can be easily plotted. Now, for the icons from a classification run, you have accuracy, committee vote, sense, specificity, class pairwise AUC, kappa error. And then if you click on one of these icons, you'll see an AUC curve for each classifier. And then here you would specify in the feature selection, you specify the input features that are going to be used for classification. And then you obviously have to select class. And then you can perform a classification run, a bootstrap bias run, and then an AUC run. And then you can also specify the number of repartitions and then bootstrap iterations. And then select which cross-validation method you want to use. And then a few other things over here, which I've shown on the right side. Now, with regard to classification output, you'll get a table. If you click on the accuracy link, you can see the accuracy based on cross-validation. This was a CV tenfold run, or tenfold CV that was run. There were 63 objects and 13 features used. And here we see the classification associated with all of these classifiers based on the confusion matrices that are padded during all the cross-validation runs and after all the repartitions that are done as well. And then ensemble majority vote, classifier fusion accuracy, and then accuracy based on ensemble weighted majority vote. And here is the spreadsheet that one would see if you click on the sensitivity and specificity. So for each classifier, you have the class, the accuracy for predicting that class, which is all the same. But the sensitivity and specificity obviously change, and so do the predictive value positive and the predictive value negative. Again, for class prediction, you can look at the committee votes for each classifier and each object, and then get the decision rules as well. There's also a class pairwise spreadsheet that you can look at. So for each classifier, you can see for all the classes involved, the AUC for discriminating between these two classes based on the input features and the data that was used. And then for every classifier, you'll get an AUC curve that has the class pairwise comparisons, and this is the AUC value, and then smooth curves for AUC. For classifier diversity, I mentioned kappa and error before. And then for each possible, or for all possible pairs of classifiers used in a run, you get a kappa value and an error value. And then you can simply make a plot of kappa versus error and look at the diversity of the classifiers employed.